interesting operations working with vectors. So up until now, if we review kind of real quick, we've been talking about in the beginning section, we're just saying, okay, well, what the heck is a vector? What's the point of working with a vector there? And what a vector does is it gives us some kind of directed distance. So we know we're starting someplace, going someplace else, what direction are we going in, how long it takes to get there. We had vectors in 2 dimensions, but then in the next section, talk about them in 3 dimensions. But the idea was they are just another way of describing directions. And that's not quite it. Yeah, I guess I'll look up. So on the bottom of page 10, we had a bunch of properties for working with vectors here. I'm not going to go through all of them. But the idea is we can kind of do math with vectors here. They're really just ways of telling us sets of directions. So if we think about like what vector addition does. Vector addition is saying, okay, you're going to do one set of directions and then do another set of directions and then add those together. Subtraction would be pretty similar mathematically to stick subtraction signs in there, but if we kind of geometrically think about it, we're going to do one vector and then basically do the opposite of the other one, so move in the opposite direction from there. We know that when we multiply by a scalar, when we do that scalar multiplication, the idea here is we're taking some distance, and if c is bigger than 1, we're going to stretch it out and make it longer. If c is smaller than 1, we're going to shrink it and make it shorter, but it doesn't change the direction. And so that's how we went through and started to define parallel vectors. Parallel vectors, we said, were scalar multiples of each other. And we use that to find collinearity, which was a question Stephanie has, so I'll try to remember to get to it, which is here. And then a couple other things, too. Unit vectors, length is just 1, and we're going to see how that comes up. And it's a very handy thing to work with unit vectors sometimes. But all of these things are just different ways of describing that direction that we're working with there. So everything we've done so far is just focusing on adding, subtracting, or multiplying by a scalar. And there's a reason for that. So in 11.0, we're talking about dot product. And then 11.4, we're talking about the cross product. But we know either way, what does product mean in math? Multiplication. So we have 2 different ways we're going to multiply. And if you think about like symbols you use for multiplication, when you first learning math, you have a little cross, a little X that you use, and you kind of get away from that and use a dot. And here they both come back again. So they're going to mean different things in terms of vectors, dot product and cross product. 11.3, talk about the dot product first. And then, like you can see, after we spend some time on there and work with that, we'll talk about the cross product. And hopefully, as we get through talking about both of them, we can kind of see how they're similar, how they're different, and when they show up there. So, page 13. We're going to go back and do a little bit of review of the adding, the multiplying, division by scalars, and then we'll actually talk about the multiplication piece in general. Okay. And the homework that's due this week, I'll double check, make sure it's all posted just fine, but it'll go over both this section and next one. So just all the dot product, cross product stuff should be on this week's homework. All right, so we've got 2 vectors in 3-dimensional space. Vector u is given by 4, -1, 8, and vector v is given by this guy over here. Okay. And remember, they're always going to be in the direction x, y, z, so it tells us to change in x, change in y, and then change in z. We're always going to stick with that order there. So adding them, how do we add 2 vectors?
Just like this.
Right, just add them by component. So the x component, add those together, the y component, add those together, and the z component, add those together here. So if you think about what that's basically doing, and say, okay, well, we're going to do these directions. We're going to go from the origin, because remember also, whenever we're in this component form, it means we're starting at the origin. It's really as a point, that's okay. So we're going to go from that point, and we're just going to add the other vector onto there. So x plus x give us 4 plus 0. The y plus the y is -1 plus 11. And the z plus z is 8 plus -7. So we end at 4. That's a funky looking 4, sorry. 4, 10, 1. And that would be the sum of those 2 vectors. Okay, I won't worry about graphing them, but if you were to imagine kind of graph these, vector u, you're going to start at the origin and move in those directions. And then from the end of that, you're going to do what vector v says to do. Just think of another set of directions, and then where do you end up? That's where we have that point right there. What about if we say multiply v by 3/2? I mean, mathematically, what is that going to look like? Sorry, my pen's all funky. It keeps kind of writing weird. So we're just going to distribute, like you said. I'll leave it in component form for now. And so 3/2 times 0 gives us 0. 3/2 times 11, 33 over 2. And 3/2 times -7 is -21 over 2. And so in terms of like what this visually represents, what what visual thing is happening here. If we take vector v, multiply it by 3/2, what are we doing to it? We're stretching or making it longer. So it's going in the same direction. If we were to start at 0, 0 and do just that vector v, multiplying by 3/2 just makes it longer, but the direction is still exactly the same there. So I leave some space here, but I'm not really going to write anything. It's more of a discussion. So multiplying, how can we multiply vectors? If I said multiply vector u and vector v, how do we do it? How so? How do you mean? So like using those u and v up above, what numbers would you plug in?
I guess not. Looking down, I guess not.
Yeah, it's kind of difficult because you could kind of think about like Adam. You can take, you know, the x times the x and the y times the y, but then do you leave that as a vector? Do you do something different with it? Like what do you kind of do with this?
It looks like almost like a product rule for making for integration.
So looking down at like the definition that gives just below there, that's what you're looking at.
That's fine.
So but okay, so this is how we start off there. It's simpler than the product rule for integration, I think, which is nicer than this. But that's going to be, so if you look below, that's going to be one way that we define going through and doing this. But we're also going to have another way of going through and doing this too. So it kind of depends on what we're trying to get in multiplication. The interpretation of the dot product is a little fuzzy. I put a link in there, I'll bring it up in just a minute, but it's not like, oh, you do this and it means this. It doesn't have like some, you know, easy to understand meaning there. The cross product, the result does kind of mean more. The answer you get, there's more interpretation time. We'll worry about that later there. So at this point right now, we're just going to say, okay, well, here's the math behind it. Don't worry so much about what the number means. I'll try to explain it briefly, but the dot product is a lot more going to be used for getting to an answer later on, not so much the number that we actually get there. But the difficulty is if you're trying to say multiply two vectors, there's not really an obvious way to take these two examples, these two vectors from up above. And I'll just write the dot there since we're going to do it in a minute here. Okay. There's no obvious starting point or stopping point here. We can kind of see maybe where multiplication couldn't fit in, but there's no thing that says, well, what do you do with that if you multiply? You just leave this bunch of separate things or something else there. So the first way we're going to define multiplication of vectors is this dot product. Okay. Same thing works to 2 dimensions, 3 dimensions, 4, 5, whatever. It's always going to be the same pattern that we have here. Essentially, what we're going to do is we're going to do like we started off with addition. We're going to say, okay, take the x component and the x component and just multiply it together. Trying to just multiply them together there. But you'll notice that what do we do once we have the x components added and the y components are multiplied? After we multiply the two products, we add them up. So what's our answer going to be to something like this? Are we going to have a vector or are we going to have a scalar? Yeah, we're going to get a scalar out of this, which is kind of weird. Okay, we take two vectors, we multiply them, and we no longer have a vector. And that's okay. Like I said, I'll try in just a minute to maybe briefly explain what this means here, but we get a scalar out of this. So the algebraic process is pretty simple. It's just multiply two numbers, and sum. Add them both together here. So we get a scalar out of this. And you can see for 3 dimensions, we've got the x components, the y components, and the z components. The process is the same. Just multiply the similar components together and add them. So it's not very difficult to find. But like I said, the meaning behind this is a little weird. So instead of me trying to explain it, this guy at Better Explained does a really good job of explaining some of the concepts that we cover. So I'll refer back to it a few times throughout class here. But this is one where he does a really good job of going through and explaining it. And of course, my page crashed, so I don't have it. So if you search just Better Explained dot product, he goes through. I'm not going to go through and read all of this. But what we're doing here, you see this little section, he has dot product. So adding vectors is just accumulating growth. Okay, we're doing the same thing. You do this, you do it again, you just keep adding those things together. Multiplying by a constant, like we know, is going to make this thing longer or shorter. So it's, he says make an existing vector stronger. I wish he'd just say like a different length, but that's basically the idea there. It's just, it goes for a further distance with a stronger vector. What the dot product does is it applies the directional growth from one vector to another growth. And so what we're going to end up with is basically this how much stronger may the original vector. So think about the dot product as a measure of how much stronger this first vector is if we multiply it by the second one, which is kind of weird. Like I said, he goes through and tries to explain it. I'm not going to go through this video. You're more than welcome to do it. But he talks about some things that we haven't seen yet. But he does go through some pretty good examples talking about numbers. And then he starts introducing totally different things like tripling your bananas and destroying your oranges. But if you want an understanding of kind of what the dot product is, I don't want to provide that because he does a much better example. So feel free to go through and read through here. Eventually, he ends up talking about Mario Kart, which is also pretty interesting there. But the dot product is going to give us a scalar. So it's a measure of how much stronger did this thing get if we multiplied it by the other one. Okay. But mathematically, it's going to be fairly straightforward and easy to work with here. Okay, but I do suggest reading this page. He does a pretty good job with it. It's a measure of how much stronger the original vector is now that we've applied that second one to it. So another operation, working at math, we need to kind of make sure we define the properties. Can we commute it? Can we associate it? Can we do all these different things with it? So again, just not so much the meaning behind this, but just the application of the math side is what we're focusing on here. The top of the next page, some properties. Some of them are obvious, some of them are not so obvious. First one's just commutative property. If you've got two vectors, your dot product in them, or it doesn't matter. U dot v, v dot u is the same thing. The second one's moving over, multiplying by 0, just gives you 0, which should make total sense. If you're multiplying a vector by a bunch of zeros now, then we know we're going to get 0, so let's get it to 0. You've totally killed the strength of that vector. The third one is just the associative property, or sorry, not the associative property, distributive property. If we have u dot the sum of those two vectors, we can distribute, and that would be just fine. The fourth one's a little less obvious. We're going to go through and prove this one in just a minute. But the fifth one says, okay, we're applying scalars. Now, pay attention here. Are we distributing in that fifth option right there? That fifth number property? Is that distributive property in that fifth property?
No.
No. Okay. Just like with multiplication, if you have something like this you're trying to solve here, you don't do 2 times 5 and 2 times 7. It's all just multiplication. Okay, so the same thing is happening here. Multiplying by a scalar, taking the dot product, it's all still multiplication. You are not distributing in a case like this. Distributing is for when you have addition there. Right. So we know that, it's just make sure what vectors are still paying attention to it. So again, most of these are pretty obvious, but that fourth one really isn't. I have vector dotted with itself and equals magnitude squared. I mean, maybe it does make sense, but I'm guessing for most of us it's not as obvious as the rest of them. But proving it is really simple with the definition of dot product. So let's look at a real quick proof here. It won't take much room, even if I know I didn't leave it. So start off with what it said. We are taking the dot product of v with itself. Okay. If we let vector v, let's get some component form. Let's say vector v is just some number v1 and then some number v2. We'll just do it in 2 dimensions, but you can do this for more and the proof is still the same. Okay. So that means by definition, what we said with a dot product is we are taking v1, v2, dotted with itself. Okay, so just writing out the component form of these vectors. And then we haven't done this with numbers yet, so it's our first time doing the dot product. But like we said, when you do the dot product, you're going to take the x component times the x component. In this case, you have to do the same thing. So we're going to have v1 times v1. And then we are going to add to that the y component times the y component, which again happens to be itself in this case, so v2 times v2. So it's just the definition of dot product applied to this thing right here. Oops, this first one should say v1. I'm sorry, I wrote the wrong thing. I said it, but I wrote it wrong. Those should both be v1. We know anything times itself is just that value squared. I did it again, so that should be v1 squared plus v2 squared. Does that look familiar? Remember, we're trying to get to, we're trying to show something with magnitude. Does that at all look like the formula for magnitude of vector? Yeah, it's like the distance formula, just missing the square root there. So it's kind of a weird thing to do, but if we want to add that square root, we'll have to make sure we square to keep the value the same here. And you may not need to write this step down if it kind of makes sense from there, but these two things would be equivalent. Okay, we have some positive sum here. This is the same thing, just putting that square root on there. That makes it more obvious why this is the distance formula. Okay, what we have in that square root is just the magnitude of vector v. Okay, that's the definition of it, and then we went through and squared it. Okay. This property isn't going to be useful so much in like doing math as doing proofs. It's just nice to have this connection between a vector dotted with itself and its magnitude. And so we'll see it show up in some proofs later on, but it's not going to be something we use a whole lot by itself. Okay, it's really not that difficult to find magnitude, so why have to do a dot product? This is a different way to do it. Okay. But let's actually do some dot products with numbers here. Okay, maybe we should have done this in opposite order, but that's okay. So example 1, we've got 3 vectors, I'm sorry, all just in 2 dimensions, so 2, -2, 5, 8, -4, 3. You can imagine if all these start at the origin, they're just kind of going off in different directions. And remember, the answer to a dot product isn't a vector, it's a scalar. So what it's saying is, okay, if I take u dot with v, if we do this vector u and then multiply it by this other vector v, we're getting a measure of how strong one of these vectors is. We don't really care about the meaning right now, just go through the math. So let's do it. So I like to write them in component form. If you don't need to do this step, that is a-okay. If you'd rather write them as a linear combination of ij and k, do that too, but this is just a little more concise. So definition of dot product, we are going to take the x component times the x component, and then add that to the y component times the y component. And so the algebra then is fairly simple. We're going to have 10 minus 16 or negative 6. So again, math isn't hard. It's just a different thing, something we haven't done before. And eventually we'll get to application of this and start using it. Right now it's just be able to go to the math. Okay. Why don't you guys try these instead of watching me go through them? So go ahead and try them. There's a couple different ways you can work through these things here. Order of operations still applies. So like if you wanted to dot product of u, v first, you already have, and do w, or use the properties above. Just take some time and try them yourself, and then we'll look at the answers and move on. Okay. So we will see how to use dot product to do a lot of different things. One of them is finding the angle between vectors. We're talking about projections. Maybe we'll get to it today. Maybe it'll be next time there. But it shows up a lot in just the behind-the-scenes stuff there. So like I said, it doesn't have a lot of application by itself, but it really helps in doing other things here. So we're going to go through the proof for this and kind of see where it comes from. If you remember the law of cosines, will make a lot more sense. We'll do that real quickly here. But the goal is to say, okay, we've got some vectors. There's some angle between these two vectors here. If you make them both start at the origin, both in component form, there's some angle between these two vectors. And let's call it theta. Nothing too crazy. Okay, so what is theta? How can we find the angle between these two vectors here? We'll also see this show up a lot in application, and it has some other uses besides just like applied problems too. So here is the formula for it. You can probably imagine getting cosine by itself or theta by itself here isn't going to be too difficult, but what the heck? Where does all this come from here? And then we can just look at it and use it. That's not really a challenge. But at this point in your math career, you need to kind of understand where things are going here. So by definition, it is just the dot product of these two angles is equal to the magnitude of both angles times the cosine of theta. So if we were to get theta by itself right on the next page here, but this is just a scalar. This is just a scalar, so we can divide both sides by that number here. What's we're going to get that left-hand side of scalar or a vector? Scalar. So we have number divided by number. We just have a number out of there. It's just going to be the arc cosine of whatever that thing is there. So find the actual value will most of the time just approximate the calculator. But where does this formula come from? So why do we bother using this? So like I said, proof is going to rely by law of cosines. It's not something we use a whole lot here, so a real quick little review of the law of cosines is. And let's just use this triangle instead of drawing anything up above there. So we can imagine connecting the two endpoints here. We have a triangle. Okay, kind of looks like a right triangle here, but the nice thing about the law of cosines is it applies for any triangle, right triangle, not right triangle. It's still going to work out here. So let's say that the magnitude of vector v is a. Let's say the magnitude of vector a is b. Just to make the law of cosines a little cleaner to write here. And what we're going to have over here, oh, I'm sorry, this should be C. Let's write it as C so it matches up with my notation. Sorry, changing magnitude of V to C. It really doesn't affect things too much. But let's call this hypotenuse, I shouldn't call it hypotenuse, this long side over here A. In terms of vectors, what is this? So in terms of U and V, what is this length here?
Which one?
So I want to know this guy right here, across this long thing right here. Let's put a little arrow on it. Doesn't really matter which way the arrow goes. I'll just put it on that end there. I want to know in terms of vectors U and V, what is this pink vector? What is this thing?
What is the size? Strength of the vector.
I'm thinking too hard about it. Okay, well, let's just do this. Is A going to be a scalar multiple of U or V? Is it going the same direction as these two guys? Is it parallel to either of them? No. No. So we know it's not just a multiple of V or a multiple of U. Is it the sum of the two vectors? If you imagine doing vector v and then scooting vector u to be at the end of it, is that going to give us A? No, but it's fairly close. What A is going to give us is based on the difference between these two vectors. And the way I have it drawn here, it'll be vector u minus vector, or vector v minus vector u, and then its magnitude is the length of A there. Okay, so that's a little kind of weird to see, but if you kind of think about what's happening here, vector addition and subtraction is we're going to do this vector v first. We're going to do that direction. And then when I subtract vector u, we're basically going to backwards and do the opposite of u. So instead of going up in that direction, we're basically going backwards in that direction here. So imagine this is like my vector u, the opposite of it. And if you imagine, my line's not really drawn to scale here, but if we take this guy right here, okay, that should be pretty parallel to this pink line here. Just kind of shifted it around. Remember, vectors are equivalent as long as they have the same length and the same direction. They don't have to start and stop at the same point here. So we're shifting these things around to wherever they're handy, but we can imagine doing vector u and then doing the opposite of vector, or doing vector v, and the opposite of vector u is going to give us this other side of the triangle here. Okay, so even without that, the proof still works out. Just trying to explain a little bit why that's the difference between them. Okay, so anyway, we've got this triangle. We've got A, B, and C. What the law of cosine says, for any triangle, when I have A, B, and C, we have that A squared is going to equal B squared plus C squared, which looks really similar to the Pythagorean theorem, minus 2 times BC times the cosine angle A. I should have wrote that in here too. Angle A is going to be our angle theta. If you took trigger pre-calc, this probably was covered in that class. It's not something that gets used a whole lot, and we're not going to use it really after this, but it makes the proof this easy as possible. And a little bit of naming conventions. Maybe you remember that the angle and the side length are usually numbered the same opposite each other. So angle A is opposite side A, angle B is opposite side B. These are the other ones. And if you really want to remember, you can write this a whole bunch of different ways for this, and this isn't going to matter, so don't bother with it in your notes. But you can also write this 2 times A times C times cosine of B. It's got all these different variations of it. You can write it for C squared. We're just going to do it for what's handy right now. Okay, so that's the law of cosines. It says this is true for any triangle, right triangle, whatever. It's going to hold true there. Okay. So in terms of our vectors, really all we're going to do is plug in that magnitude of u, magnitude of v, all that stuff there, and then just simplify this down until it looks like this. Okay, this is really what's responsible for what we're doing there. So here we go. Let's do some substitution. We said that A is the magnitude of these guys squared. So we're going to have the magnitude of v minus u squared equals b. We said b was the magnitude of u squared plus c, so magnitude of v squared, and then just keep plugging these parts in here. So minus 2 times magnitude of u times magnitude of v times cosine theta. So all we've done is just write the law of cosines in terms of our vectors instead of in terms of A, B, and C. All right, so let's use our properties of things up above that we just talked about, and let's fix this. Let's just focus on this left-hand side for now. Okay, we'll go back to the right-hand side in a little bit. Let's focus on this. If you think back to the properties up above on the top of this page, we said that taking the magnitude of vectors squared is equal to what?
B1 plus B2, or B1 squared plus B2 squared. It's the distance formula. I don't know what.
Yes, distance formula. But look back to the properties that we just covered on the top of this page here, specifically property number 4. We said that the magnitude of vectors squared, so we had v squared equals what in terms of dot products? Right. So we're going to use that same thing here, only now instead of b being our vector, it's the difference between these two guys here. But the same thing is still going to apply. So we're going to have v minus u as our vector, dotted with itself, is equivalent to this left-hand side here. And I'll note C property 4 above. So if you want to see why these things are conjunct, it's just that definition that we said. The one that I said we're not really going to use a whole lot besides in proofs, here it goes. Okay. So by definition, the magnitude squared is the same thing as a dot product of that vector with itself there. Okay. We're going to use another one of those properties to basically distribute this thing a couple times here. So this property right here says that I can distribute this vector, and I'm going to do it in phases. So I'm going to take the first one and multiply it by the first vector, and then you multiply by the second vector. What we can now write this as, so think about this as that whole thing u up above here. We're going to have that first set of parentheses dotted with v, then minus that first set of parentheses dotted with u. So we're taking this whole thing and distributing it to v, and that whole thing and distributing it to u. Okay. You could also just FOIL if you like FOIL. That's really all we're doing is just foiling this thing out.
Why? I mean, I guess it is just proofs. But if that was the case of this stuff, why wouldn't we just do, like if you had our component forms, why wouldn't we just subtract first? Square.
I would if I had the numbers.
Okay.
If we had numbers, I would totally do it that way. If I had numbers in place here, I would not do it this way. I would do just what you said. I would subtract them and find it that way. We could work this that way, but once you start with little v1s and u1s, it just gets messy. So for a proof, this is a little easier. But yeah, if you had numbers in component form, I would totally subtract numbers. Okay. All right, let's distribute one more time so we can actually see why this is like FOIL. So now distributing again, we're going to take vector v times v. So v dot v, and then vector v times u. And since it's commutative, it really doesn't matter what order you write the u and the v in. Just make sure you have that dot there. And then similar to the second half, distribute this guy. Oops. And minus and negative might have a plus 2 dot u. So again, you can kind of skip that middle step. If you're cool just saying FOIL those vectors, that's really all we did was FOIL those two vectors there. Okay. So we're going to distribute each step here. Like I said before, I'm not going to expect you guys to replicate proofs. Okay, I mean, some Calc 3 teachers will, and if you go on and that's important, then I apologize. But I think the application was more important. However, I want you to kind of see behind the scenes and maybe be able to make some sense of it there. Okay, know that this stuff isn't just mumbo jumbo. It's based on maybe no. All right, so use our definition, distribute, distribute. Now let's just clean this up a little bit here. So C, still from property 4 up above, we can now go back and rewrite this. This is the magnitude of v squared. Okay, that's just what property 4 says. The vector dot over itself is its magnitude squared. These middle two are the same terms. So like normal, it's combined like terms. We have minus 2 times v dot with u. And then similarly over here, a vector dot of itself is the same thing as that vector's magnitude squared. Okay, so all we did there was just kind of clean things up a little bit using that property. All right, let's drag down that other side that we haven't done anything with yet. And we are almost done. I know I'm about out of room here. Hopefully you got a little more room on your notes, but we're about done. Oops. So copying all that stuff from before just down here. Can we do anything to simplify this equation?
Cancel out the squares.
Definitely. Okay, we got a lot of stuff I can cancel. There's a v, magnitude of v squared on both sides. So if you want to go through the long process of subtracting that from both sides, go for it. I'm just going to cheat and say, yeah, those two things cancel out. Okay, similarly for the magnitude of u squared. I can subtract magnitude of u squared from both sides, but those things are also just going to cancel each other out. So then we're left with this negative 2 v dot u and the negative 2 magnitude cosine thing, right?
Right, so why aren't those all on the
Okay, we're super close to the end here. I will go back and rewrite this. If you're comfortable without rewriting this step, that's fine. Computers have an infinite amount of room, so it's easy for me to rewrite things. Okay, so there's what we have left so far. Both sides are multiplied by a factor of -2, so let's just divide by that and get rid of it too. And so you can see there we're left with what's up above. Okay, that is where this formula comes from. Now I wrote them in the other order, but it's commutative, so it's okay to flip it around there. But that's where this comes from. It is just the law of cosines with some algebra applied to it. Now, like I said, we don't all just use the law of cosines all the time, but there's nothing really crazy to where this thing comes from. But knowing the angle between two vectors is very useful. Okay, we'll look at some example of numbers in just a minute here, but it's going to be something that shows up quite a bit, and we'll refer back to this. We're going to develop a really easy shortcut of something to see here with this. It's going to show up quite a bit later on. Okay, but anyway, that's where this comes from. It's just taking that law of cosines and applying it to this triangle made up of vectors instead of just a regular triangle. Okay. So like I said, really what we care about is knowing theta. That's what we're trying to get to here. So here's that same formula copied above. Solve this guy for theta. Magnitude of u is just a scalar, so let's divide by that. Magnitude of v is just a scalar, so let's divide by that on both sides. So anything divided by itself is just 1. Okay, for that. Can I do anything to simplify the left-hand side? Not really.
Is that a unit vector?
Yeah, they're unit. We said something. They're unit vectors. I don't know if that's what you said, but it sounded like it. They are unit vectors, and you could do something with that. If you think about this piece right here, that is just a unit vector in the direction of u. If we had a shorthand notation for that, we totally use it, but we don't, so there's really nothing we can do here. But don't try to cancel these things out. Just because we have a u on top and u on bottom, they don't cancel out. That u in the numerator is the vector u, the u in the denominator is the magnitude of u. So one's a vector, one's a scalar. So yeah, so we're just stuck with the dot product of two vectors over the product of their magnitudes. Equals cosine theta. I like stopping here because arc cosine is an awkward thing to work with, but technically to get that theta by itself, we take the arc cosine on both sides. And if you're one of those people who'd rather write cosine to -1, that's fine too. Okay, our book uses arc cosine, so I'll stick with it, although I know most calculators don't. So arc cosine on both sides, and then just copying that one more time. Okay, like I said, I like leaving it like this just because I don't know. I just do, but that's technically getting theta by itself. This will work for two-dimensional vectors, which are pretty easy to picture. This will also work for three-dimensional vectors, which aren't quite as easy to picture. That's what we're going to do an example of down here. Okay, so we're given 4 vectors u, v, w, and z, and we want to find the angles between the pairs of vectors listed here. So we'll do the first one together, and then the second two you guys can do is just kind of algebraic examples, but we'll use those to discuss here. So to find the angle between the two of them, we're really just using either this formula, if you like arc cosines, or you can go back to the other one there. So let's say I like this one here, so we're going to use that. So cosine of theta is going to be the dot product of u and v. So I'm going to write this out in component form. So 3, -1, 2, dotted with vector v, which is -4, 0, 2, all over the magnitude of each of those vectors. So when we find the magnitude of vector u, we're going to have 3 squared plus -1 squared plus 2 squared. And for vector v, -4 squared plus 0 squared plus 2 squared. So all of this comes from vector u. Don't put on the pen. And all of this comes from vector v. All right, so let's finish that out there. So again, dot product, that's our real new thing for this section. How do I find the dot product in that numerator? Walk me through the math. What's it going to be?
3 times -4, and 1 times 0.
Make sure you are adding all those little products together. We get a scalar. Dot product gives you a scalar. And whether you work that out or jump down to the denominator, whatever you're more comfortable with, I'll do it in pieces here. So denominator, it's going to be 9 plus 1 plus 4 under the square root, and then times square root of 16 plus 0 plus 4. Okay. So -12 plus 0 plus 4 over square root of 14 times square root of 20. We can keep working that, or we can, so what is that? -8 over, well, someone can simplify those down faster than I do with my calculator, let me know, but I'm going to open up my calculator here.
14.
Yeah, but if you multiply 14 by 20, you might be able to do something with it. All right. Whoops, oops. Okay. All right, so square root of 14 times square root of 20 is really all I'm trying to simplify here. Square root of 14. Square root of 20. Reduces down to 2 root 70, so it didn't really do a whole lot, but 2 times the square root of 70, so we get the denominator. So 8 and 2 are divisible, so we get negative 4 over the square root of 70. The reason I like leaving it in cosine theta equals form instead of finding the arc cosine all at once there is when we get an angle that we know the exact answer of, I can get an exact angle. Anytime you can get an exact answer, way better than getting an approximate answer. However, does 4 times or 4 over the square root of 70 match up with your unit circle at all? The nice things you know about the unit circle? Yeah, not even close. So we're going to have to approximate this one. So we're going to have theta is the arc cosine of negative 4 over square root of 70. I don't really care if you leave it in radians or degrees, just label your answer. Radians are a nice default, especially for upper level math, but degrees are fine too. I think my calculator right now is in degree mode, so I'm just going to leave it as is. So arc cosine. I am clicking the wrong buttons. There we go. Of negative 4 divided by square root of 70. So there's the exact answer, which is horribly ugly. I don't want that. I want this approximate answer. So the approximate answer is 118.56 degrees. And in radians, I wrote in my notes there, that should be about 2.07 radians. So even though these are three-dimensional angles and we can't just like picture them, we know that if we just draw 2 lines in space that start at the same point, there's an angle in between those. We're going to make a plane, there's an angle in between those. There we go. That's an obtuse angle in this case, about 119 degrees. Okay? So nothing too fancy about those 2 angles there. All right, you guys try B and try C. We've got about 8 minutes left, should be enough time to get through this and just discuss real quick. So same thing there. If some of you want to try C first and some of you try B, that's fine. Then we can look at our answers together. But same thing. Find the angle between those pairs of vectors. No.
For the homework, did you want us in radians or degrees?
I think usually it defaults to radians, but check the problem. If it wants it in degrees, it should tell you, but default to radians. Your answers for B and C should work out to be much nicer numbers, which means you should be able to get an exact value for the angle.
Or 8.57 degrees. That's right. Pretty. That's a really good. No, you got. I don't know how.
All right, let's go ahead and discuss. If you're not quite finished, if you got at least one of them done. So for B, what does the angle between the two vectors equal?
Pi over 2.
Mm-hmm. Or if you like your degrees better, that's the same thing as 90 degrees. So what can we say about these two vectors? Like, these two vectors are what to each other? Yeah, they're perpendicular. Good. I didn't want to tell you the answer. Okay, so if we have 90 degrees, we have a right angle or perpendicular vectors here, okay? The fancy word for what we're going to call this is orthogonal. That's what it's not parentheses, my C's, but not like. So orthogonal vectors here. But the definitions in the notes in just a minute here too, without the parentheses. Okay. What'd you get for C? What's the angle between those two vectors?
I can get the angle below
Mm-hmm. And if you think about your unit circle, that should match up, right? Yeah, that just turns out to be pi or negative pi if you really like, okay? Or 180 degrees. So how do these two vectors compare to each other? Think about them visually. What are they going to look like?
opposites.
Yeah, one's going one way and one's going the other way there, but they just basically form a straight line here, okay? So it doesn't have a special name, but they're opposites here. This is going to be specific here. This piece B here, this is going to be super helpful, okay? When things are perpendicular or orthogonal or form right angles, we've been through enough math to know that's special. Okay, when things are perpendicular, they have special relationships, special properties. There's a really easy way of telling if these two things are perpendicular without even having to go through all these steps here. Think about the process you use to find that cosine. We said, I'll just go back up to this thing right here. The cosine of theta is dependent upon the dot product, okay? What'd you get for the dot product of those two vectors in B? The dot product of the vectors in B is 0, okay? 0 divided by anything, who cares what the lengths are? 0 divided by anything is going to give you 0. So a shortcut we basically have here is any time the dot product between two vectors gives you 0, you're always going to have perpendicular vectors. Because when you go through this process here, 0 divided by anything, regardless of the magnitudes, is always going to go through and give you 0 here. And so that's going to be really, really helpful for us here. I could have wrote that much more efficiently, but I didn't. Okay, the dot product of U and W is 0, and that's kind of how we're going to have our quickest way of finding orthogonal vectors. Sure, you can go through and do this every single time, but it's kind of silly to go through those steps because we know we're going to get 0 out of this. Okay. So real quick, just to summarize this stuff here, top of the next page, you basically just said that. If you want to write it again, go for it. Okay, what can we say for the vectors? They have a dot product of 0. So here's going to be kind of our shortcuts for assessing this. In two-dimensional math, we like to say, okay, how do you define parallel lines? How do you define perpendicular lines? And then what else happens about the case here? So with vectors, we can do the same thing. We can say that two vectors are perpendicular if their dot product is 0. Because what we just saw, we define the angle between the two vectors as the dot product divided by the lengths. If the dot product is 0, we know we're going to get a 0 out of this, and then the steps we follow there. So it's basically just a shortcut. Okay. How can we define if two vectors are parallel?
If they're
We've got kind of two ways we can do this.
I mean, if they're dot product or I guess the standard unit you say is the same on top and bottom.
Okay.
Or no, opposite.
This is true. We could definitely go back and do this. We can say, okay, we'll follow a similar process what we see in C, but think back to the previous section. How do we know if two vectors are parallel in the previous section? Scalar multiple. And that's still going to be the easiest way to go through and do this. So yes, this still works, but the easiest way to see if two vectors are parallel if they are scalar multiples of each other. Okay, and yes, we could go back to the angle thing and look for pi. Also, if the angle between the vectors is 0, we know they're going to be parallel or going in the same direction. That would work, but this is faster, and we've got to have a fast way of doing this. Okay, so either way would work, but that would be a fast way. If this doesn't happen, which most of the time this doesn't happen, most vectors are not perpendicular or not parallel, they're going to intersect at just some other angle. But when we do have these properties, things work out nicely. So we'll kind of do things a lot here. Okay, so even though, like we just said, you could go back and think about the angles between them to find being parallel, remember, the easiest way to decide if vectors are parallel is just a scalar multiplication. Okay, once you've got them in component form, if they're the same, well, you're done. Otherwise, look for them being scalar multiples of each other. Okay, so we're going to use these two ideas to help us with not direction cosines, but on the next page with projections, but we are out of time today, so we'll talk about that next time. If you've got questions, please let me know, and then I'll double check and get the homework posted pretty soon so you can get work on that. Okay, so that's that. Enjoy the rest of your Monday, and then we'll see you guys in the morning. What was that? Oh, no question. Stephanie, what were you going to say?
You had asked me to say something about number 17.
Yes. So, let me see. This. All right, I went back. I don't have extra copy over. Let's start. Okay, I think what you answered on 15 was correct. I don't know why it didn't like the way you wrote your answer, because the way you typed it should have been okay.
I didn't have any space. Yeah, that's why, because the spaces weren't there.
But for 17, so here's just the work from the book. I'll leave that up since we don't have a whole lot of time here. So to show these things are collinear, they did the PQ and the PR and the same way we did in class, and their numbers might be a little different. But any two combinations you pick should be the same. Just make sure they have the same starting point. So if you did like QP and QR or something, that should be fine too. We want just the same starting point if possible. But when you go through and do this, we get this combination for one of them, the other for the other. And like I said, we're looking for some scalar multiple. And the easiest way to find that is I say just pick a pair of numbers, like the 28 and the 8. What do I have to multiply one by to get to the other? And then see if that works for all of them.
Oh.
So as long as you pick the same starting point and then just find a multiple that works, you're just going to check and see if it works for everything.
Okay. I'm just going to go ahead and copy that down real quick.
Go for it. I'll leave it up there while you write it down. We're just going to finish with chapter 1 and then watch the video. I'll get you the notes tomorrow for chapter 1. Okay. All right. Anything else, Stuart or Stephanie?
Not that I can.
But yeah, so that one that you email me your answer to, I'll go back and double check. It's almost right. I can give you the point for it. We'll just figure out if you couldn't figure out yourself why it didn't enter right, then we'll get it figured out for next time. But it looked like it did. Okay.
All right. All right. Thank you.
No problem. Have a good day, Stephanie.